All right, folks. Section 3.4 is called the chain rule, and it's the next basic derivative rule that we've got to learn. All right. I say basic. It's a little bit complicated. It's necessary when the function that we're trying to take the derivative of is itself a composition of functions, meaning that we've got maybe one function plugged into another function, and we're trying to take the overall derivative. All right, called the chain rule. Function composition, that's one of the ways that we can combine, that form new functions from old functions. So that's sometimes the way they phrase that in a pre-calc book. So if we've got two functions, let's say f of x and g of x, right? There's lots of different ways we can combine those. We can combine them by adding and subtracting them, right? So polynomials are things like this. They're power functions that have been added and subtracted. And we can multiply two functions or divide two functions, or one function by another, rather. All right. And so we had our sum and difference rules. There were rules for taking derivatives of combination functions like this, and they were in 3.1. Right, section 3.1, we studied the sum and difference rules, and those were the easy ones, right? Kind of just distribute that derivative, just go term by term, easy ones. For multiplication and division, it was a little bit more complicated because we had to consider the product rule and the quotient rule, right? Which we just covered in section 3.2, we covered those rules, right? So we covered those things. The other way that you can combine them, though, is besides just adding, subtracting, multiplication, and division, is what we call function composition, right? And we use that little circle. There were some pre-lecture exercises about composition of functions with their domains and so forth. And so if I've got f and g, I can form f composed with g of x, right? And another way to write that is f of g of x. Right, and so when we see things that look like this, whether or not we see the notation that looks like this is one function, g of x, plugged into another function, f. And so overall, we've got a composition of functions, okay? So the way I want to do this is first I want to just work through an example, right? Because the notation gets a little bit heavy. I'm going to work through an example, kind of just do it the way it's meant to be done, explain what I'm doing, why I'm doing it, the places I'm putting the different pieces, and then at the end, then we'll backtrack and I'll state this generally in terms of the formula with the different types of notation that we might use, okay? So I want to do something though. I want to create a function that's something like this, sort of one function tucked inside of another function. All right, just to match the book here, I'm going to call my function a capital F of x. No big deal. If you want to call it a little f of x like we normally do, that's fine. If you want to call it g of x, or you want to call it a k of x, or any letter you want is fine. When I try to make this jive with the notation in the book, I'm going to want lowercase f's and g's. So let me just say I've got some function. And let me just do something like this, something real simple. Let's say I've got 5x squared plus 7x cubed. So something simple like that, a polynomial. But let's say, so that's a function itself, which if we want to get real basic, is a sum function, right? But we're considering that one function that we could take the derivative of easily right now using our derivative rules from section 3.1. Suppose that itself is wrapped in parentheses, and maybe that whole expression is being raised to another exponent, right? Let's say something like a 8, right? Just making up these numbers. So let's say I've got something like that. Okay. So now I want to take the derivative. So I want to find f prime of x, pulling a capital F prime of x. So you're looking inside these parentheses and you're thinking that's a polynomial, and I know how to take the derivative of a polynomial. So I probably want to do that at some point, and that's going to be part of our answer. And you might also be looking at something like this. I'm covering this up to kind of imagine that it's one number right in there, one figure, one unit, and I've got something in there being raised up to the exponent of 8. So I'm also thinking I've got this inside polynomial, but then I've sort of got this outer function of like something raised to the 8th power. And so I feel like maybe I want to bring that 8 down and decrease that, so kind of use a power rule also. All right. So bear with me for a second. I'm going to go ahead and call this inside piece something else. I want to introduce another letter, just something to call that, and I'm just going to use the lowercase letter u. Okay, so I'm going to say let u equal the inside of this thing, 5x squared plus 7x cubed. All right, and at some point we're going to need to know what the derivative of that is for this formula, and we're ultimately taking the derivative. So yeah, let's just find the derivative of that thing. And so now that's just a polynomial. I call that the inside function because it lives inside of these parentheses, but that's just a polynomial. So let me take its derivative, and I'm going to call that derivative u prime. Okay, so we got u prime, and this is just a combination of power rule, constant multiple, sum rule, right? So 2 times 5 is 10. 10x, decrease that power. 3 times the 7 is going to give me a 21 up front, and with an x squared. Okay, so I got my derivative right there, u prime. That's the derivative of the inside. Since I went ahead and called that u, right, I call this inside u, then what I'm sort of looking at, this is kind of like scratch work, f without the prime. My original function of x really looks like u to the 8th. All right, so that kind of looks like what I've got, because I'm calling this inside piece u. So if I'm calling that u, then I've just got u to the 8, okay? And so here, if I want to take the derivative now, f prime, what gets tricky here is I want to take the derivative with respect to x, right? We use that phrase a lot, with respect to x. That means x was the variable in my function, right, in my formula. So I'm trying to write a new function as a function of x, but I've got this other letter here now. I've got this thing, this term u. So how exactly am I going to do that? Well, what I'm tempted to do is try to use some kind of power rule, though. I've got something raised to the 8th power, and so it seems natural that I might use my power rule on that thing. 8u now raised to the 7th power, right? And that actually is part of our derivative. That's what we've got. So let me write that what I've got over here. So if I'm calling that guy u, what I'm looking at right now is 8 times this original piece right here, 5x squared plus 7x cubed, and decrease that power from an 8 down to a 7. Okay? There. What we've just done, I call, is taking the outside derivative, sort of the derivative with respect to like the most outer thing that we've got. So I kind of start on the outside and sort of work in. So we took the 8 down out front, decreased it, boom, we've got the derivative to that. And that's what we're looking at here, just in a little sort of more concise notation with that u right there. That's almost done. You could argue that's half of it. But we never use the derivative of that u, right? It seems like we should be using this, all right? And we do actually want to use that. What I need to do here is not just 8u to the 7, but then I need to multiply that by what I call the inside derivative, or the derivative of that thing, the derivative of this thing, which is this, which we're calling u prime, all right? So that's actually, this is what the chain rule looks like spread out for this particular function right here. This particular function. That's the way it's going to work. So you kind of take the outside derivative, leave that piece alone, right? I got that original piece right there, and then multiply by, and then put the inside derivative, or what I'm calling u prime here. All right, so let me put that. All right. And then now we'll just try to wrap up this problem, okay? Then once we wrap it up, I'll put up the sort of the actual notation that shows how this works. All right, that's our final answer, though. Okay, can I clean this up at all? So if you enter this in WebAssign, they might accept it. I know some classes, this one not so much, but I know when I used to teach Math 24, was a TA for Math 24 Business Math, they do a lot of derivatives like this with these rules, and they do a lot of chain rules. And those homeworks and exams and things like that were multiple choice. And this would not be an answer that's listed here. Because even though this is correct, what they would do is they'd want to clean this up a little bit. They'd want to sort of distribute what we can, or what's easily distributed, to simplify this as much as possible. So let's talk about what we can't do, and then what we can do, and then what we should do. Maybe argue that. First of all, we know what we can't do simply is take this 7 and get it inside these parentheses. Right? Sometimes students are tempted to do that. They want to distribute the 7 to both of those things. But that doesn't work like that, right? If you've got a plus b to some exponent n, that is not equal to just a to the n plus b to the n. Right? Not true. You don't distribute an exponent over an addition or subtraction. Just doesn't work. What you've got to do is write out several of these terms, right? A plus b, and then FOIL them together, distribute them together, right? So that's what you'd have to do. So if you wanted to do anything about this 7 exponent right here, you could, but what you need to do is write this guy out 7 times, right? 5x squared plus 7x cubed 7 times, put them all together, right? We don't want to do that. You could, we don't want to, we don't need to. So leave that alone. But don't make the mistake of trying to do something we can't do with that 7, right? So we just leave that alone, that's fine. And typically what I recommend is, even if it's an exponent of a 2, you could probably leave it alone. But you could probably also FOIL that together quickly, easily, not terrible. But I usually think factored form like this is actually better. But if it's anything higher than a 2, exponent of 3, 4, 5, 7, 9, whatever, just leave it, right? If it seems like it would be unreasonable to FOIL all those things out, don't do it. This set of parentheses, so a couple things to notice here. These parentheses are necessary. Why? Because I'm multiplying by the entire derivative u prime, which is that thing separated by a plus sign. You need those parentheses, because if you draw that without parentheses, which folks do a lot, what that means now is take this piece, multiply it by 10x, right? So you've got that, but then you're just adding on that, right? There's no multiplication by that, but really we're multiplying by that entire thing. So those parentheses are necessary right there. Now though, those parentheses don't have an exponent on them, in this case. They don't have an exponent on them, meaning those numbers are kind of free. It's not like I'd have to rectify anything like here by distributing anything out. That is what it is. And this 8 being multiplied, I can jumble around the order that I'm multiplying 8 times this term, and I can actually get that 8 in there, right? I can take this constant and distribute it into there, and that's usually recommended to kind of clean this up as much as we possibly can. So let me do that. 8 times this 10 is going to give me an 80. It's going to appear in there. 8 times 21 will be 162. All right. Is that right? Is that how many baseball games are in a standard season? It is. Okay, so we distributed that 8. There we go. Cool. So we got our final answer. So distribute what you can. Big, heavy exponents, leave them alone. Cool. Chain rule. First example, done. Okay. So that was the process, but let me get some notation up there so we can help to remember how to do that process in the future. Yes. So let's think about what we had here. We can come back to the U idea because sometimes we'll do this with U. This rule is actually written in the book. It is page 198. And it's stated twice using the prime notation and then the D notation, right? The D dx. The D notation is actually really useful for the chain rule. Very useful. When you do applications of the chain rule, like related rates, so when you get to section 3.9 and doing related rate word problems, you're going to be taking derivatives with respect to time or with respect to volume or with respect to area, right? You're doing a lot of these word problems with these physical units, and so the fraction sense of the D notation is going to be helpful. But let's first try to get it out through the through this F notation. So let me keep this example here for a second. So what you're going to see in the book is if something like this, and there's a big intro, that these functions have to be differentiable and continuous, right? There's some restrictions, so you read through the technicalities. But we're going to assume everything is nice. If I've got some function that I'm calling capital F that is set up as f of g of x, right? So in other words, I've got a function within a function. That's what this says. What would be going on over here? Well, g of x is the inside function. So if we're using this notation, what we're saying is g of x right there is 5x squared plus 7x cubed. And then what's f of x? F of x is actually x to the 8th. Right? Earlier we called that thing a u and we made some substitutions, but really what you've got is you've got these two different functions of x, and then when you compose them, if you do f composed with g of x, that's f of g of x, right? That's the way our function compositions work. And now, so that's f of g of x is our polynomial, or our cubic polynomial, that thing, right? So we get f of that thing, and then f says now take your input, right? F says take your input and raise it to the 8th power. So take your input, raise it to the 8th power. Here's our input. There we go. Okay. So this capital F right here is a composition of two functions, and there are the two functions. Okay, so good. So we've got that set up. Now, what does the derivative look like? So I'm going to try to talk my way through what we did earlier with this notation. So then, if we've got this composition of functions, then the derivative of that composition it's f prime, so the derivative of f, right, which is our outside function. So the outside derivative with respect to g of x, right? Meaning that so remember when we took the outside derivative, we said 8 something to the 7th, right? That was this. F is x to the 8th. right? And so we know that the derivative of that is bring the 8 down, decrease it to a 7, right? So that's the process that we do to something raised to the 8th power. But with respect to, not with respect to x, with respect to actual g of x, meaning that the g function still lives there, right? So that's what we saw as the result. We had this 5x squared plus 7x cubed still living there. It's kind of just coming through the ride. Right, so this f prime of g of x looks messy, but really what it's just saying is leave the inside alone and just sort of take the outside derivative, pretend that's one solid object, and take the outside derivative with respect to that object right there, right? And then what did we do though? Then we multiplied by, so we had called this u, and we multiplied that by u prime, the derivative of that. Using this notation now, we've called that thing g. And so what we would multiply by would be the derivative of that thing, happen to be that, but in that notation, in our g notation, what is that we're multiplying by? G prime of x. Okay? So it looks messy. So maybe you see why I start with the example, so we get used to doing the process. It feels okay to do, and then you look at the notation, and maybe the notation clicks, right? If you start with the notation, I think this one looks weird, but that's what we've got. Okay? That's our prime notation for the chain rule. And again, I use this phrase a lot, right? This thing was the inside function, I call that. And so g prime of x is the inside derivative, or I'll just say deriv, right? Inside derivative right there. What are we multiplying that by? This is the outside derivative. Outside derivative, and that's it. So you got an outside derivative, inside derivative. Probably don't see that language in the book, but to me it's intuitive. I like that phrase, those phrases, so I use that a lot. Okay, there we go. That's one set of notation for this. This video is pushing 17 minutes. I'll probably try to get the next notation up here, though. Let me just continue this video, so this one will be kind of long, all right? Then maybe I'll do another example or two in a follow-up video. So we've got that. How can the D notation come in handy? Okay, for that, I could still call that F. So I could call that F. I could call it F of X, because it's a function of X. So I could call it F of X. I could just call it F, which looks a little bit strange. Or let me just call it Y, actually. Okay? Just to emphasize that we do this often, where we just want to find the derivative of Y, which is y prime, right? Want to find deriv of y with respect to x, right? So you could say y of x or something like that, which is y prime. We're going to see that a lot, so get comfortable with thinking that if you've got a function, this is still a function. The fact that I'm not using function notation, it's still a function of x, right? We could argue that the graph still satisfies what function, the requirements it needs, and I'm just kind of calling it y. So its derivative is going to be y prime. It's going to be big in the next section, implicit differentiation. Okay, so we want to find y prime. Y prime, remember, is the same as that means the derivative of y with respect to x, right? That's the denotation. So y prime is the same as dy dx. So I'm trying to take the derivative of this thing. So sort of a preview to what you're going to do in the next section, implicit differentiation 3.5, is if this is true, that y is the same as this, right? Y is the same as this thing. That's what the equals mean. Then I'm going to apply the differential operator to both sides, right? Both sides are the same, so if I do the same thing to both sides, I should get the same result. Meaning I'm going to take the derivative with respect to x of both sides. Well, if I do that on the left-hand side, d dx of y, I'll clean that up in a second, and then over here I want the derivative with respect to x of this thing. 5x squared plus 7 x cubed to the 8th power, right? So again, we use this denotation to sort of indicate what we want to do, what we're about to do, kind of like we did with limits. So I want to take the derivative with respect to x of this. That's my goal. Over here I've got this, d dx of y, right? But another way that you might see that is just put the y up top, sort of like as if we were multiplying fractions. If I had 1/2 times 3, right? Where does that 3 belong? Well, 3 is 3 over 1, so the 3 really lives up top. Same idea. That's why this notation is cool. So the y lives up there. So what we're finding here is also dy dx, right? That means the derivative of y. So if y is equal to that, then of course if we take the derivative of that side, right, then we're going to get dy dx. So that's all this notation is doing here, right? This is my function y. I want to take its derivative, so then this is the name of it, right? That would be what the derivative is. This is what we're calling it, which is y prime. Okay, so we're setting that up. Okay, let's take that a little bit further though, because what I'm trying to take here though, this is where the u situation comes in. Let u equal that inside piece, 5x squared plus 7x cubed. Okay, that's the inside piece. I'm using the letter u as sort of an intermediary function. Okay, when we did the example earlier, we took the derivative of that, which I called u prime. U is a function of x, right? So u prime is really du dx. Again, two different notations, but they mean exactly the same thing. So here, u prime, u is a function of x, so if we take the derivative with respect to x, and we had this derivative earlier, 10x plus 21 x squared. Okay, so we've got u, we've got du. All right. So let's think about what we've got now. We are trying to take dy, we want to figure out what this is, dy dx. All right. What we're looking at is y at this point is equal to u to the 8, right? By making the substitution, I'm claiming that y is no longer, it's sort of within there. U is a function of x, right? So here, ultimately, y was built as a function of x. X is the variable that builds y, right? But x builds this piece inside, which we're calling u, and then u to the 8th really builds y. So there's that sort of intermediary piece. So what we've done right here is we've shown that y is expressed as a function of u, but I want to find the derivative with respect to x. So how can I do that? So dy dx, this is what I want. Let me write this. What if I had dy du? And then so I'll write this out, then we'll try to interpret what these things mean. Dy du, and multiply that by du dx. Okay? The question is this true then? I wrote an equal sign there. Do you guys believe that dy dx is the same as that thing? This is where the coolness factor of, wow, these things look like fractions comes into play, right? If these were fractions, right, if you had 1/3 and you're multiplying that by 3/5, you'd say, well, wait a minute, look, the 3's cancel, right? And so it's just 1/5. So kind of collect them like that, right? The notation works that way. These du's, you can kind of visualize if you cancel them out, then what is this result equal to? Then all you've got left up top is dy, and then what you've got left in the bottom is dx, okay? So I'm kind of forcing this little product here of this dy du and then du dx, but it makes sense that if those guys cancel out, we're left with dy dx, which is our y prime. That's what we're looking for, all right? And so this right here, that's the chain rule. I've got this derivative, and then I've got times that derivative. Outside derivative, inside derivative, right? Multiplying them. So it's different notation, but it's the same thing. So let's try to clean that up, though. Show what we've got going on here as far as specifics with this function. Okay. So this is true, and remember, this is y prime. Dy dx means the same as y prime. The derivative of y, that's what we're looking for, right? The derivative of our original function. So what we're told right here is that it's equal to, well, what's this? Du dx, we found that over here, right? Du dx is the derivative of u, which we call the inside piece. That's our inside derivative, which we had earlier. So that's my 10x plus 21x squared that we found earlier. That is this thing right here. What is dy du? That's the one that looks a little bit weird, right? But that's not really that weird, because y was this thing, 5x squared plus 7x cubed raised to the 8th. Looks complicated, but then we called that whole thing u, right? So y, I'm turning this blue, but this over here said y equals u to the 8th, right? So since we represented y as a function of u here, then it makes sense to take the derivative of y with respect to u, right? Take it with respect to the variable that we see right there. And that's the power rule on u to the 8th, which u to the 8th is 8u to the 7th, right? That's our derivative. That's it. And that's what we did earlier. As a final answer, does that look good? No, because our original function was a function of x, so we're using this u as the intermediary. But at the end, our final answer should be a function of x again. And so, yeah, we take the derivative of y with respect to u, derivative of u to the 8th, which becomes 8u to the 7th. And then what do? Plug the original u back in where it belongs. And let me just squeeze it on in there. 5x squared plus 7x cubed. And then we got this 8 out front, the 7 as the exponent. Color code these guys. And then what did we do last time, right? This is exactly what we had. We distributed the 8 inside there to clean it up, but this is our chain rule right there, okay? So this rule, kind of looking sloppy on the board, this right here is the chain rule expressed in D notation, okay? Earlier we had the chain rule expressed in prime notation. Whatever you like is cool. This one, really helpful for setting stuff up. And again, these aren't fractions in the sense of a ratio of numbers, like as what we typically think of a fraction represents. But the notation behaves like fraction notation. Really cool sort of innovation, I guess, in the way this stuff works, these pieces. So there we go. Kind of a long video right there, but that's really the chain. That's as far as it gets. I'll probably post one video of like a extremely nested function, meaning a function plugged within a function in another function, right? You could pound them on in there. So maybe I'll follow up with that, but there you go, is your chain rule. Alrighty, guys.